Greetings, everyone. Let's talk about vectors in a 2D plane, okay? Not to be confused with just vectors in space and things like that, because we're going to only talk about vectors that can exist in the same plane in this section and the next section, specifically for the trigonometry aspect of it, okay? So let's start with what a vector is, okay? A vector, geometrically, just looks like a line segment with an arrow on one end. You may even call it a ray from geometry. But the actual meaning behind a vector is much more than that. When we're using vectors, the arrows that we draw are meant to be some sort of action. Okay. Now we're just going to be throwing vectors around left and right here so that we can practice all the mechanical processes and analyses of these things. But most of the time when you're using vectors, there's some sort of action or meaning behind each vector. For example, vectors can be used to represent forces. Okay, so you'd have an amount of force with a direction that the force is pushing, right? There's two pieces of information there. And that's exactly what vectors can give you. They're directed line segments when you draw them on graphs and things, but they're actual, physical actions or objects. And they bring two pieces of information, like a force would, a direction and an amount of force, right? In this case, a length and a direction would be the vectors that you draw. Vectors can be used for things other than forces. They can be used for field lines. They can be used for velocities. They can be used for representing a position of something. Most of the things in reality that need vectors have more than one piece of information, and that is always represented with the size of the vector and the way that the vector is pointing. Okay, so that's basically what a vector is. A lot of times, and pretty much all the time, whenever we're using vectors algebraically, we'll write them with some sort of arrow over the name of the vector, and that's to remind you that it is an actual vector and not just a simple number. A lot of times variables that are equal to numbers can be added with other variables and things like that. We put the arrow over a vector quantity so that you don't get it confused with just a plain number quantity, because those can't be combined most of the time, adding and things like that. Okay, now vectors can be a single letter, or sometimes you'll see them in double letters. And the reason that you would do double letters like this is if you were representing a vector as a beginning and an ending point. So this would be vector V, and this would be the vector between points P and Q, specifically from point P to point Q. So you could call it vector PQ, okay? Now the length has an actual name in vector terminology. We call it the magnitude or the size of the vector, okay? This can be geometrically viewed as the actual length of the line segment, and realistically, the magnitude or the length or the size of the vector is how much stuff it's carrying with it. So if this were a force vector, it would be how much force, how many newtons or whatever you're measuring in, does that force carry with it. If it's a velocity, the magnitude of the velocity would be the speed. If it was the position, the magnitude would be the distance from some sort of origin or displacement. Okay, regardless, the magnitude of the vector is the size of it, how much stuff it has with it. Okay, the way we write this is with these double bars. It look like absolute value almost, just two of them, like this or like this. Okay. Now, of course, vectors are a little bit different than numbers. Okay, I can actually draw vectors anywhere on a grid, and as long as I don't rotate the vector or change the length of the vector, I can actually still say it's the same vector. In other words, vectors are equal or equivalent as long as they have the same length and direction. The actual position that the vector is on your grid or around your objects or whatever doesn't actually change the vector. You can slide vectors all over the place and it would still be technically the same vector. Okay? let's look at some examples of all of these different calculations. I have three vectors up here for you, okay? Vectors v, u, and w. And I have them labeled out as the vector between 2 points each time, but I've only labeled them with single letters just to make it simple, okay? So what we want to do in this example is show that v and u are equal vectors, okay? That's kind of obvious, right? You can kind of see it. I tried to measure it out and get it, nice and equal. But remember, in math, just because it's drawn up there and it looks the same doesn't mean it is the same, right? So we actually want to prove that those two are equal vectors and that w is not, right? Obviously w is not. You can see it's pointing in a different direction, but we're going to show that that's actually true, okay? Little side note, the direction of a vector can be represented as a slope or an angle, okay? Later on, we're going to do a lot with angles, right? We're doing trigonometry. But for now, I'm going to use the slope because it's a quick and easy way to talk about which way a directed line segment is pointing. Okay, if you're reading it from left to right, slope is just a rise and run calculation, and you can show that two lines are parallel or not, right? Because they'll have the same slope. So for this example, we're going to calculate the lengths and the directions of all three vectors, and then we'll show that v and u are equivalent. Okay, so how would I get the length of the v vector? Well, v vector is between the point 0, 0 and 3, -2 right here. So that would just be the length of the line between the 2 points, which from algebra is just your distance formula between 2 points. So I'll be doing the square root of 0 minus 3 squared plus 0 minus -2 squared. Just the distance between 2 points. That's all it is. And then that is going to be equal to 3 squared is 9, 2 squared is 4, and 9 plus 4 is the square root of 13 here, like that. Okay? So now, vector u up here is the vector in between -2, 4 and 1, 2. So same type of calculation. I'll be doing a distance between 2 points. That'll be -2 minus 1 squared plus 4 minus 2 squared. And notice here we'll get -3 squared, which is 9. And 4 minus 2 is 2 squared, which is 4. And 9 plus 4 again is 13. So I have the square root of 13. So that's one little hat tip to that v and u are probably equal. They have the exact same length, the same magnitude, right? Let's do the magnitude of w now. Okay, the magnitude of w is between these 2 points. And so that's going to be -5 minus -1 squared plus 1 minus 2 squared, which is going to be equal to, I've got -5 plus 1 is -4, squared is 16, plus 1 minus 2 is -1, squared is 1. 16 plus 1, 17, so square root of 17. Okay? So w is definitely not equal to the other two already, because the length is not equal, right? Okay, so the direction of v. I'm going to use the slope to do this because it's something I can get out quick and still show that it's a direction that a line is facing, right? And also, if two slopes are equal, if two lines are parallel, right, it's the same thing. So that's what we're going to show here. The direction of v, then, is going to be the slope between the points 0, 0 and 3, -2. So that's just going to be y2 minus y1, right? -2 minus 0 over x2 minus x1, 3 minus 0, and I'm getting a -2/3. Right? Remember, that makes sense. A negative slope is something that from left to right is going in the downward y direction. Okay, the direction of u, same thing again. y2 minus y1, so that's 2 minus 4 over x2 minus x1, that's 1 minus negative 2. So again, I'm getting negative 2 over 1 plus 2 is 3, right? So notice these two slopes are equal, which means that the line segments are parallel, and therefore their directions are equivalent. Their lengths are equivalent, their directions are equivalent. Because of these two facts, I can then say that those two vectors are equal, right? So vector v and vector u, not only do they look the same on the grid, they are mathematically equivalent. Let's do the direction of w real quick. So y2 minus y1 over x2 minus x1. 2 minus 1 is 1, and negative 1 plus 5 is 4. Okay? Again, it makes sense that the slope would be positive because w is facing in an upward direction when reading from left to right here, right? Let's talk about another way of displaying vectors algebraically. It's called component form. And basically, the vector can be thought of as two different dimensions, an x dimension and a y dimension. Okay? So all I'm going to be writing down is for the x part of the vector, I'll be basically x2 minus x1, the run of the vector, right? The what it runs across. And then the vy will be y2 minus y1, which will be the height, the rise, if you will. Okay? So it's just like what we were doing a minute ago with the slope, right? This would be the rise, this would be the run, technically. But I'm keeping them as separate components so that the vector can be displayed in this format. And I'm using these pointy braces here, call them the vector brackets. Okay? The magnitude then, using the distance formula, is I'm just going to square the x component, which is x2 minus x1, and square the y component, y2 minus y1, add those together and square root. That's still the same distance formula. It's just condensed now because I've already incorporated those pieces in the components of the vectors, right? So this is still the same formula. Also, once I have it in component form, it's much easier to discuss vector addition and scalar multiplication of vectors. These are operations that we'll be doing a lot with particular vectors that we'll be using all the time. Okay? So here's one way of thinking of the vector addition. If I'm going to do it with the component form, all I'm doing is combining x components and combining y components with the addition that goes along with them. Okay? And what does it mean geometrically then? When I add two vectors, I can either do what we call the parallelogram format, or I can do tip to tail format. Basically, when you're adding vectors, you have to remember that I'm not just adding numbers. Also, that directional information is built in there. So when I'm adding two vectors that are pulling away from each other, for instance, like this, right, then I'm going to have a vector that comes through the middle, right? Or if I'm having a vector pull one way and then pull another, one vector plus another one, right? Then basically you can just split the difference between them. If I go tip to tail, right? Tip here, tail here, like this, then basically I could have just done one vector action to go from this beginning to this end. Either way, it's sort of the same idea. Scalar multiplication is whenever I want to multiply a number times a vector. And this is very particular. We can't usually combine numbers and vectors, they're different. But I can do this one thing where I'm combining a number with a vector, and it's scalar multiplication. All it basically is distributive property, where I'll be multiplying that same number, whatever k was, I'll be multiplying it by each of the components, okay? All it does is it stretches or compresses the size of the vector, hence the term scaling, right? All I'm doing is changing the size. Scalar multiplication absolutely can never change the direction of your vector. It only makes it longer or shorter depending on the scale number that you pick. Okay, let's get some examples of all of this algebra setup. Here's our three vectors that we were just talking about, right? U, V, and W. Let's get the component form of each of those vectors, right? Okay, so V is the vector from 0, 0 to 3, negative 2. So V is going to be 3 minus 0, comma, negative 2 minus 0. In other words, V is going to be the vector 3, comma, negative 2. Not to be confused with the point 3, negative 2. That's why it's in the pointy vector brackets. It represents an action, a motion, or a force, or whatever. 3 is one component, negative 2 is another component. Okay? It's not a point. Vector U is the vector 1 minus negative 2, 2 minus 4. Therefore, I have 3, negative 2. Do you think that's a coincidence? We just showed that those two vectors were equal vectors, right? Well, notice in component form, they are exactly identical. Not a coincidence. They are the same vector, period. They are exactly the same vector. Doesn't matter where they are in the grid, they are the same vector. They are describing the same kind of action. W is then negative 1 minus negative 5 and 2 minus 1. So then I've got the vector 4, 1. Okay, so that's the vector for W. Now let's go through and do a couple of the algebraic combinations that we were talking about here. For example, vector addition, right? Right here, I want to talk about the vector addition between V and W, right? I drew it out, but let's actually go through and do the addition here. V plus W, right? Vector V plus vector W is going to be 3 plus 4 and negative 2 plus 1. So V plus W is equal to the vector 7, negative 1. Okay? Well, look at it geometrically now. If I take vector W and slide it over so that it has the same beginning point as V, right? Notice it's still the same vector, right? It still goes over 4 and up 1, over 4, up 1, over 4, up 1, right? It's the same vector. I just slid it over so that their tails can be the same. Well, that's like this. The parallelogram method of adding vectors. If I put their tails together, then making the diagonal of the parallelogram is going to be their addition. So if this is W and this is V, I draw the parallelogram. This line and this line are parallel. This line and this line are parallel. Notice exactly what I get. 1, 2, 3, 4, 5, 6, 7, down 1. Which is exactly what we calculated, right? Over 7, down 1. That's the vector addition. Or, if you want to do tip to tail, same thing. Just slide V over to the end of W here, so that the tip of W is on the tail of V. Notice, tip to tail, it still hits that same ending point. I'm still adding this way, right? So to vectorially add like this has directional information too. Don't just put the vectors next to each other. That's not how it works. You have to keep the vectors pointing in the correct directions. Or if you're going to do the algebra, you can simply add components. Scalar multiplication, again, emphasize, scalar multiplication cannot change the direction of a vector, only its length, its magnitude. Okay? So here's what happens here as an example. Here's vector v. I'm going to calculate the scalar multiplication of 3 with vector v. So 3v, basically. Right? Okay. 3v is equal to 3 times the vector 3 comma negative 2. So 3v is equal to 3 times 3 is 9. 3 times negative 2 is negative 6. So 3v should be the vector 9, negative 6. Well, count it out. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. So 3v is exactly that. And notice, I drew them out with a ruler and everything so you could see they are 100% on top of each other. They are pointing in 100% the same direction. Scalar multiplying that vector did not change the direction. It merely made it longer in this case. We could have also made it shorter, but 3 is bigger than 1. If I had multiplied by something like 1/2 or 0.2, whatever, it would have made the vector shorter instead. Okay? In that same light, let's talk real quick about vector subtraction. Okay? Basically the same thing as vector addition. However, we have the subtraction, of course, right? Which means instead of adding the components, I will be subtracting. And of course, the order does matter in that case, right? You don't want to reverse the subtraction. Ax minus bx, ay minus by, okay? But the geometry that comes in here is important, okay? And there's two different ways to view the geometry here. When you want to subtract two vectors, one way that you could visualize is that I'm adding a with the opposite of b. Basically, I'm using a scalar multiplication of -1 times b. And all it does is it gives me the same exact length of b, but it's pointing in completely the opposite direction. They call it anti-parallel. So this is b, and then -b is anti-parallel of b. It's pointing in the other direction, same length. If I vectorially add a with -b, parallelogram method, I get this vector here, which would be a minus b, a vector minus b vector. Okay? Now notice another way to do this is to realize that that's parallel with connecting the two tips here. So if I've got a and b both butting from the same point, right? Then basically I can just connect their tips. And you want to let the subtraction point in the direction of the leader of the subtraction, right? So in this case, he's pointing at A, okay? And if you think about it, that needs to make sense, because if I add A minus B plus B, I should get A back, right? So from tip to tail, right? B plus A minus B should give me A. And it does, right? Because it's pointing in that direction, okay? So an example, let's do the same V and W vectors as before, but let's do V minus W. So the algebraic component form, easy to do, 3 minus 4, -2 minus 1. And I get -1, -3 as my V minus W vector. Okay, so first way, if I do the anti-parallel, the opposite of W, negative W, is going to be -4, -1, right? Okay, so right here, you see W. Here's negative W, right? Here's W. There's negative W. So if I add negative W and V, I get this vector here, right? Which is -1, -3, going left and down. Left 1, down 3. Or the other way, if I simply take the two vectors, W and V, and connect their tips here, right? And notice it's pointing down because V is the leader of the subtraction. So I'm pointing at V. You'll notice that those two are parallel and the same size, right? Either way, it's the same subtraction. From W, I'm going left 1 and down 3 to get to this point here. So that would be V minus W also. Real quick, some properties that go along with the mechanics of using these operations, just to sort of keep your mind pumping here, okay? Whenever you're adding vectors, the order doesn't matter, right? They do commute. U plus V equals V plus U vectors. Also, they are associative. If you're adding vectors in one format, then adding them in a different format still gives you the same result, okay? There is such a thing as the zero vector. The zero vector is the vector where zeros are the components. Not to be confused with the number 0. The zero vector is an actual vector with components that are all 0. Okay? So if I add the 0 vector to another vector, no change. If I add a vector with its opposite, the antiparallel, same size, opposite, then you get the 0 vector. If you multiply two different scalars, then you may as well multiply the scalars together first, then multiply by the vector. It's the same result. If you are adding the addition of two scalars, then it's the same as if you were to scale the vector two different ways and then add the results later. If you were to scale a vector addition, then it would be the same result as if you were to scale each individual vector and then add the results from that. The 0 number times a vector gives you the 0 vector. This is a 0 number, this is a 0 vector. Don't get those confused. And if you want to look at the length of a scaled vector, then it's the same as if you took the original length of the vector and multiplied by the absolute value of the scalar number. And that only matters if k is a negative number, right? One more reminder, if you're trying to add a number and a vector, you will fail. It has absolutely no sense behind trying to do this because a number and a vector are completely different objects. Not only do we not add them, to even write something like this has absolutely no sense behind it whatsoever. Now we need to talk about special cases of vectors that are going to come up all the time. One big one is unit vectors, okay? A unit vector is any vector with the length of 1. So it gives you 1 unit of something. Now these are important because they represent the direction information mostly. Having 1 unit of something basically just says, here I have a unit, and then all I'm concerned with is which direction is it pointing. You'll find that in a lot of our vector applications, unit vectors will come into play when I want to deal with directional information and leave out magnitude information. Okay, so first let's get an example of a unit vector. Here's an example. I know it looks kind of yucky with the square roots, but here's how I can tell you that it is a unit vector. If I do the magnitude of it, that means to square each of the components, add them, and square root, right? So if I square root of 6 over 3, right? Square root of 6 squared is 6, 3 squared is 9. And if I square root of 3 over 3, square root of 3 squared is 3, and 3 squared is 9. Then they have a common denominator, so 6 plus 3 is 9. 9 over 9 is 1. Square root of 1 is 1. So this vector has an actual length of 1, a magnitude of 1. That makes him a unit vector. So then whatever application we were dealing with, we would be more concerned with the direction that this little a vector is pointing. Okay? Now there are some special unit vectors out there that we use quite often, and that is the I and j unit vectors. Okay? These are also sometimes called component vectors because I is the vector 1, 0, meaning that I have nothing but 1 in the x direction only, 0, y, and vice versa. J is the y component vector. No 0 for x, no x direction, 1 in the y direction, 1 up in this case. Okay? And the reason why these are so nice is because I can take any vector in component form and rewrite it in what we call ij or ij component form or some other variation of that name. So if I have the vector from before, v is 3, -2, right? Then I can rewrite that as 3i minus 2j, right? Notice I've got the little hats on the I and j so that I don't get that confused with like complex numbers or anything like that. Those are special unit vectors. They get the hat instead of the arrow. Okay? Now in some cases you might see a little arrow and that doesn't mean it's any different. This is just typically what I've always seen. Okay? Now another application is to create a unit vector. Okay? This is something that will come up just as much as the special component unit vectors. I want to preserve the direction of some vector, but I want to take away its magnitude, right? So I'm going to create a unit vector of the A vector, right? All you do is you take the vector itself and then divide it by its own length. Think about where you've seen something like that before in division, right? In numbers, if I divide a number by itself, you get 1, right? So that's essentially what I'm doing here, but just in a more complicated, more moving pieces type of format. I'm dividing something by its own magnitude. So the actual magnitude is going to shrink down to 1, but it's still a vector. Technically, this denominator is a number because it's a magnitude, it's just some number, but the top part is still a vector. So basically, all I'm doing is a scalar multiplication with division, right? I'm scaling the A vector down to a length of 1 to make it a unit vector by dividing by his own length. Okay? But it's still a vector. Let's do an example. Let's say I have some big B vector, 5, -7. Okay? Well, first, I'll compute his magnitude. So magnitude of B is equal to square root of 5 squared plus -7 squared. So that's going to be 25 plus 49, right, under my square root here, right? So then I have the square root of 74 as my length of my magnitude of the B vector there, okay? So at this point, if I want to make the unit vector of B, right, maybe I'll nickname it something like U. Or you could call it little b, or, it just depends on your situation. Here, I'll just call it U. Then that's going to be the vector 5 over square root of 74, comma, -7 over square root of 74. At this point, you can decide to rationalize those denominators or manipulate them to decimals or whatever. But nonetheless, this represents an actual unit vector. Okay? Now it's difficult for me to draw something like that, especially with the decimal numbers. Take a look at this GeoGebra for a second so that you can get a good visual of how this is a unit vector. So let's look at this in a more accurate way, drawing-wise anyway. Notice what I'm going to do is I've drawn a unit circle here, right? So any unit vector should fit inside of this unit circle. That's how we'll know for sure that it is a unit vector, because it will go from the center out to the edge of the circle. So the first example, little a, the vector square root of 6 over 3, comma, square root of 3 over 3, we computed that to be a unit vector because it has length 1. Notice it does actually fit in the unit circle, right? It's pointing in this direction, and it does go from the center out to the edge of the unit circle. So the other example was big B, the vector 5, -7, which you see it does go 5 over, right, 7 down. This is the vector 5, -7. So if I compute the length, we'll call it capital L, equals the length of vector B. Remember, we calculated square root of 74, which is actually the 8.6 that you see here. Okay? If I create
little b to be the vector big B divided by its own length L. Notice I do actually get, let me go ahead and change the color so you can see a little bit better. I do actually get a vector here. You can see the little red one there. I'll turn off the big one. See this little red unit vector here? It's from the center out to the edge of the unit circle, so it is length 1. It is a unit vector. More importantly, it's completely 100% parallel to big B. And that's exactly what we want. It's just a scaling of big B down to a length of 1.
Next, as promised at the beginning, we can talk about the direction of a vector using angles now. Okay? And I bet you've been wondering this whole time also, hey, when's the trig coming in, right? Here we go. Here's some trig involved with the vectors, right? So, as we stated before, magnitude of a vector is the square root of the sum of the components squared, right? That hasn't changed. And that makes sense to look at the way that the components, the rise and the run are the components, right, are arranged with the actual vector itself in a right triangle. So it makes sense that this would follow some sort of Pythagorean setup. Okay, well, continue on. Since this is in a right triangle setup, there's an angle that can be represented in standard form from the positive x-axis up to your vector. So the vector is the terminal side of an angle. And then that angle can be computed by solving the equation tangent of the angle is equal to the rise over the run, the AY divided by the AX. Components, right? Because it's opposite over adjacent. Vice versa, if you know the angle and the magnitude, the length of that line, I can compute the components AX and AY by doing magnitude times the cosine of the angle and magnitude times the sine of the angle. And that would give me the components of some vector that the angle and magnitude represent. So it just depends on which way you want to go with this, whether you want to find the angle or use the angle to do your vectors. Okay, so here's a couple of examples. I have vector B here, again, 5, -7, and they want you to re-express this vector as some magnitude with some direction. Okay, so let's get a general feeling for vector B here. 5, -7, right? That means that it's going to be 5 to the right and 7 down. So it'll be something like this. I mean, I'm not exactly, graphing it to scale there, but you get the idea. That's the B vector. Okay? Well, pay attention to the quadrant, right? I should expect my theta to be this. That should be theta B. Something from quadrant 4, right? We've already computed the magnitude of this one. We did it in the last problem, right? We already know that the magnitude of B here is square root of 74. Great. Same as before, right? 5 and -7. Okay. So I need to set up the equation to find the angle now. Tangent of theta B here is going to be equal to -7/5. And then you just need to go back to when we were talking about solving trig equations. That's all this is. And I set it up with the tangent first. Notice I didn't automatically say this is equal to arctangent. Okay? You got to be careful. Arctangent is only defined for quadrants 1 and 4. And I know this is quadrant 4 that we need, but it's not defined in the way that we want to talk about it. Right? The arctangent would give me the negative angle over here if I did arctangent of -7/5. So what I'm going to do is just like we do in solving the trig equations, I'm going to say that my reference angle is equal to arctan, the inverse tangent, of just the 7/5. And remember, we always do that because all I want is the size information of the angle, the size of the angle here, right? So arctangent of 7/5 in degrees, we'll just do degrees for now, as we do with most of the time with vectors, right? Arctangent of 7/5 is equal to 54.46. So I'll use 54.5, right? Approximately 54.5 degrees. That's the size of the reference angle. Now remember, we're in quadrant 4. So theta B is approximately equal to 360 minus 54.5 degrees, right? So then that's going to give me 305.5 degrees, right? Okay. So then, if I were asked, express vector B with a magnitude and a direction, I would say vector B is the vector with magnitude square root of 74 in the direction of 305.5 degrees standard position, right? Standard being from positive x-axis all the way around. So you would just have to feed those two pieces of information, right? The magnitude and the angle, the direction angle, okay? Vice versa. What if you have a vector that you've been given the magnitude and the direction angle, and it's asking for the component form? Well, that's why we have these, right? Straight up. Let's graph it real quick though. 130 degrees means that our vector should be in quadrant 2, right? So not drawing to scale again, just like before, but I should have some vector that's pointing like this, right? Such that the angle here is 130 degrees. And of course the size is 5. I want you to see how computing them this way takes care of the whole thing. I don't even have to think about the quadrant and so on from there. I can simply just do the computation. So here, zx, right? Because I'm doing vector z here. Zx is going to be equal to 5 cosine of 130 degrees. And zy is going to be 5 times the sine of 130 degrees. Okay? So then let's do those two computations here. And I can say that my z vector is equal to 5 cosine 30 negative 3.21 comma 3.83. Okay? So this would be my z vector. Notice how just punching in the calculations automatically gave me a negative x and a positive y. Negative x and a positive y. And if you square those two and add them together and square root again, you will get the length of 5 again. Okay? Now, one other thing I want to add to this is that you can actually form a unit vector in this same way, right? Don't forget, a unit vector is one where the magnitude is 1, right? So automatically from these two formulas, if you were to say, give me a unit vector in the theta direction, right? This is going to come up later in some of our applications. Sometimes I just want to create a unit vector and all I have is an angle. Well, being a unit vector means I also have a magnitude of 1. So basically it'll be 1 times cosine and 1 times sine. So some unit vector, let's just say u, would then be equal to the cosine of theta, comma, sine of theta. Keep that in mind. Anytime you're going to create a unit vector, all you need to do is have an angle. And you just need to put the cosine of that angle, comma, the sine of the angle. And that will guarantee you have a unit vector. Because cosine squared plus sine squared is 1. Right? And I'll know that it's in the theta direction because I'm using the theta to create the two components. Okay? So I can actually create a unit vector in some direction right here. In fact, you could do the same thing here. Punch it up real quick. Just don't put the 5s, right? And then you'll get the unit vector that's in the direction of z, right? U of z, unit vector of z in this case. Let's go ahead and crunch that up. All I'm going to do is cosine of 130. Negative 0.64. And sine of 130. 0.766. Okay?
Let's take a look at this again. Here's that same b vector that we talked about before, and then this is how we computed the unit vector that we did before. And just now we computed the angle out to here to be that 305.5 degree angle, right? So here, let me show you how, even though I can turn this off here, I can make another vector here. We'll call it little b underscore 2. I'm going to make a vector, and I'm going to do it the same way, but I'm going to do it using the sine and cosine that I was just showing you. Notice if I do cosine of, and then I'm going to have 305.5. Now you got to be careful here. GeoGebra is going to do it in radians. So I'm doing 305.5 degrees, and then I'm going to have to multiply that by pi divided by 180. So that's the cosine of it, comma, sine of, and then again the 305.5. And then I'm going to do times pi over 180, like so. Okay, now take a look at the components here. See, this is the unit vector we made before, the red one, right? And then this is the unit vector that we just did using the 305.5 degree angle. And you'll notice the components are identical. And that's because it is the same unit vector. We computed the 305.5 degree angle for this b vector. And all I typed in for this vector was just the cosine and the sine of that angle with no magnitude. So it's going to create a unit vector there. Okay? And then also to discuss the other vector that we were talking about, the vector z. Z was the vector that had a magnitude of 5, right? So what I'm going to do is I'm going to say 5 times. See how I put that in front of the vector there? And then the vector is going to have the point of cosine of the 130 degree angle times pi over 180 to make it the correct thing there, comma, sine, again, the 130 degree angle times pi over 180. So there's our z vector. We're calling it z1 because it likes to use the letter z for the component, the actual coordinate. Notice those are the numbers that we computed before, and then the length of 5 here, right, from the center on out, and it's at 130 degrees. So notice the z vector is here. If I were to take the 5 off of that, notice all I'm doing is taking away the magnitude, and I still have a vector, right, with a cosine of 130 degrees, comma, sine 130 degrees. And what happens is I get that calculation like we did before. Notice it is an actual unit vector there. So the point I was getting at here is I can actually create a unit vector if I know an angle by doing the cosine of that angle, comma, sine of that angle. It will give me a unit vector if I do that.
So let's get an example of using vectors in a real situation. 99% real situation. In this case, since we've only done some very basic structures of vectors, then all you're going to see is that the vectors help us set up the correct situation and make sure that all of our information is lining up like it's supposed to. Okay? I am going to work this same example in the next lecture using other methods of vectors, and you can see how they both give the same solution. But for now, the vectors are mostly here to make sure that we have all of our information correct and that it does actually make sense with the given setup. Okay, so here we go. A force of 350 pounds is being used to hold a cart with some sand in it on an incline, right? So basically a ramp, right? And the 350 pounds is used to hold it. And the reason I'm being very specific about that is because if you have enough force to actually make the cart move, then it's not the same exact correlation to the full weight because you've already overcome that, right? If you've actually gotten motion with the cart, it's possible that you're using more than is necessary to overcome the weight. So basically think of it as how much force right before that cart starts moving up the ramp. Like it hasn't quite started moving yet, but it's not going down either. It's right at that equilibrium where the weight of the cart wanting to roll down the hill is just balanced out, right? So we can use that to directly correlate to the weight of the cart and sander. Okay, so 350 pounds is what's being used to keep it from rolling, and it's basically being held there, right? And it's a 21-degree incline ramp. Okay, and so we want to compute the total weight of the cart and the sand. So let's look at the setup here. You've got your ramp, right? And I'm saying that the 21-degree angle, and then you have a right triangle set up with the ground up to wherever the top of the ramp is going. Okay, and you can cut that basically however you want, and you can make that happen in your ramp. Okay, so the cart's being held there, and what we want to compute is the actual weight, right? And the weight is basically the magnitude, right? Just the magnitude of this vector pointing straight down into the earth, which is why I have it at a right angle to the horizontal, right? The horizontal here represents the earth. The incline, of course, is the thing that the cart is on. And the weight is basically your gravitational vector of a certain size. And so what I really want to compute is the magnitude of this W vector here. Okay? All right, so some key things to notice here. The 350 pounds is being pulled this way. And I'm, of course, making a small assumption here, but I'm assuming that we want to get the most effort out of our force here. So the force is going to be parallel to the ramp, right? It doesn't necessarily have to be, and in which case you could, start putting some other really cool things into the problem. But just to make the simplest, most basic thing, I'm going to assume that the vector of this force is the same direction as the ramp is. Okay, so it's at the 21-degree angle also. All right, so that also means that I can take this vector, right, and I can slide it onto the ramp and it should be exactly parallel. It also means that I can slide that 350-pound vector wherever I want, right? And what I choose to do is I'm going to choose to slide it right here next to the tip of the weight vector. Okay, now that's way far down into the center of the earth, but I can just pretend, right? I'm sliding it, and as long as I don't change the size or the angle, then it's an equal vector, right? So here we go. I'm going to slide it down to this tip right here. In other words, I'm saying that the magnitude of this little piece is 350, right? That's the magnitude of this little vector right here. Okay? Well, through some other geometry, what I can do is I can say that there's another component vector of W here at a right angle. And the reason why that's important is so that it fits Pythagorean setup, okay? But also, if I'm forming a right angle here, in conjunction with the right angles that are here and here, I can show that this angle right here is equal to the angle of the incline there, 21 degrees. Okay? And you can do that by showing that since this is a right angle, then the right angle with the incline and the blue vector here is also totally a right angle. And so then therefore you can say this 90 minus the 21 is equal to this angle, but then subtract it from 90 again gives you 21 back again, right? So in other words, I'm saying that the sum of these two pieces here would have to be 90 degrees. That's one way of looking at it. Also, you can use similar triangles, right? Set up the way that this is rotated here, okay? Or you can do subtraction of this angle with the angles over here. One way or another, you should be able to see that if I add up all the angles in the right way, that inside of this right triangle here, I've got a 21 degree angle. Okay? So all I'm interested in is the magnitude of W here. Using the 21 degree angle and the fact that this is parallel to this, sure, it's pointing in the other direction because it's a component, okay? But that just means the vector itself is negative. The actual magnitude is still the same. They're just opposing, right? If you will, this is the component of gravity that you're overcoming by balancing the cart, okay? So back to the triangle. I've got enough information in this triangle here that I can actually solve for the magnitude of W. The magnitude of W is just the length of this vector. Okay? So in other words, 350 divided by the magnitude of W should be equal to opposite over hypotenuse. Notice with the 21 there, that should be sine of 21 degrees. Okay? So opposite over hypotenuse of that triangle gives me this trig ratio. Okay? So I'll multiply both sides by the magnitude of W. And we've actually already seen this particular setup, right? We've seen that a component of a vector is equal to a magnitude times the sine. Okay? But I want to solve for the magnitude here. So I'm going to divide. The magnitude of W is equal to 350 divided by the sine of 21 degrees. Okay? So let's see if we can get a number tacked onto that, right? Let's see. 350 divided by sine 21 is equal to about 976.65. Now remember, we're talking about a force over here in pounds, right? And that's this 350. So the units will directly carry over because sine is unitless. Pounds. Okay? Now notice, I wasn't really getting a vector result there because all I really wanted to know was the total weight, right? The actual direction you could put with that is towards the center of the earth, and then you could actually have a complete vector there, right? This amount of magnitude pointed at the center of the earth is a direction, right? Okay, so I hope that this lecture has helped you in your endeavors of understanding vectors. Stay tuned for the next lecture on vectors with dot product.